Thank you, everyone. I'm sorry it's going to be a very long presentation because I'm just filling the gap that someone couldn't make this, and this is about something that I prepared for somewhere else, and I didn't know that I don't have this much time. So I just figured out that I don't have enough time. So apologies about that. So as you might know, a substantial fraction of unsupervised learning research is driven by generative modeling. And generative adversarial networks are a recently introduced class of generative models. And today my presentation is all about generative adversarial networks. Today, first, I try to address why generative adversarial networks are worth of studying. Then I compare generative adversarial networks, or in short, we call them GANs, with other existing generative models. Mainly there are two main competitors that are fully visible belief networks and variational autoencoders. And then I go through the details of GANs, and as much as time allows me, I try to explain them how do they work. And then at the end, again, if time allows me, because unfortunately GANs are very hard to train, I'm going through some known practical tips and tricks that can be used to improve the performance of GANs. So first of all, why generative adversarial networks are worth of studying? To answer to this question, let's first start with generative models. In general, we can divide generative models into two categories. In the first category, technical help.
Bit of technical help, medic.
Maybe.
The heck?
Okay.
We have liftoff.
Okay. Sorry. In general, we can divide generative adversarial networks into two categories. In the first category, that you see an example of it on the left-hand side of this slide, and I believe the majority of the audience is familiar with this category of generative modeling. The generative model takes samples from a training set. In this example, you see we have one-dimensional samples, and these samples are drawn from a distribution, which we call it p-data. And the job of the generative model is to learn to represent an estimate of that distribution, and the result is a probability distribution, which we call it p-model, and we show it here. In the other class or category of generative modeling, on the other hand, we do not estimate p-model explicitly, but we have a model that generates samples from p-model, and you see an example of it here. So we collected some high-dimensional images of cats, for example. These are the data that we use to train the generative model, and the job of the model is to learn how to represent and generate new images of cats, and you can see some examples here. So I think that I just answered one of the answers for the question why GANs are worth of studying. So there might be some cases that we need to generate samples from p-model instead of estimating p-model, and in those cases we can use generative adversarial networks. GANs belong to the second category that you see an example on the right-hand side. One of the other areas that generative adversarial networks have shown lots of potential is when we need to deal with multimodal outputs. Lauder and his collaborators provided a very good example for this, and their goal was to train a model that can predict the next frame in a video sequence. So on the left-hand side here, you see the actual frame of the next video, which the model would ideally predict. In the middle, you see the output of a model that they trained using a least mean square error. And as you can see, the quality of the generated image is not good. The image is blurry in some areas, like the eye and the eyebrow, and also the ear has kind of vanished. And that's the reason that this happened is exactly what I said. You know, they use mean square error to loss to train a model, and we know that mean square error is not able to handle a multi-modal output. So it's only able to generate one single output, and that single output is actually an average over many slightly different images, and as a result, you see the image's quality is not good. What they did next, they used an additional generative adversarial network loss, and this time they showed that the model now can understand that there are many possible outputs, and each one of those generated outputs is sharp and recognizable, as you can see an example of it in the right-hand side. Okay, the video is not working. Oh, it's working. So Zhu and his collaborators from UC Berkeley also did something very interesting. They presented their work a few weeks ago at ICML workshop, which was here in Sydney. And what they did, they showed that how we can use generative adversarial networks to convert an image to another image. You see some of the examples here. So they showed how they could use generative adversarial networks to convert a sketch of a shoe into a photorealistic image of a shoe, or convert a satellite photo into a map, or their famous video, which I'm hoping, unfortunately, I don't know why it's not working. I can't play the video. But this is their famous video, which they use again GANs to turn a horse video to a zebra video. One of the reasons that these people could do such amazing jobs is again because what we explained in the previous slide. Each one of these inputs can have multiple correct outputs, and we just said in the previous slide that GANs are very good with multiple correct outputs, and that's why they could do an amazing job. For example, for this sketch of the shoe, we can have multiple correct photorealistic images, like different images of shoes with different colors, or one in leather and the other in another material. So that's similar to the previous case. Also, Radford and his collaborators did something very interesting that I think is a food for thoughts. So what they showed, I'm going to explain GANs in more details in a few minutes, but for now you should know that for GANs the input is a vector of random variables in a latent variable, latent space, and the output is an image that we try to generate. So they trained a generative adversarial network on images of faces of women and men with and without glasses. Then they collected the latent vector that represent images of men with glasses, and then drive the mean value over those latent vectors. They did the same thing for images of men without glasses and images of women without glasses. And then what they did a simple arithmetic over the latent space. This is what they did: men with glasses minus men without glasses plus women without glasses. And then they fed the results, the latent vector that is the output of this simple arithmetic operation to the generative adversarial network. And what they could do, they could generate images of women with glasses. So as you can see, they showed that simple arithmetic operations in latent space have clear interpretations as arithmetic operations on semantic attributes of the input. One of the other areas that I believe generative adversarial networks have lots of potential is in semi-supervised learning. One of the things that I really don't like about supervised learning, especially when you train a classifier, is that you need to collect a lot of data. For example, if you have a classifier that is going to classify your data into n different classes, you need to have a large amount of data for each one of those n classes. And it's not just that, but you also need to label all of those data, and it's very time consuming and it's very tedious. So what researchers did, they combined the loss of the supervised learning loss of a typical classifier with the unsupervised learning loss of a generative adversarial network. They added an extra class to the classifier that represents images or samples generated by the generative adversarial network, and then they trained a model. But this time, instead of training the whole system with image samples or labels, but this time they just labeled a small portion of samples of each class, and then they used the rest of the data unlabeled, and then they trained the model, and they could achieve amazing results for the classifier. Another area which is quite exciting is reinforcement learning. Reinforcement learning has attracted a lot of attention by the GAN researchers, and this year at ICML we could see lots of papers that try to combine GANs with reinforcement learning. So if you're into automation and reinforcement learning, so I highly recommend you to have a look at those papers. Okay, now that I think we know what GANs are really good for, Let's compare them to their two main competitors that are variational autoencoders and fully visible belief networks. So let's first start with fully visible belief networks. I don't know how much you know, but fully visible belief networks form the basis for sophisticated generative models that we see are coming from DeepMind. Can anyone name one of those? No? Have you heard the name of WaveNet? Yes? Okay, so WaveNet is one of those generative models that is based on fully visible belief networks, and its job is to generate extremely realistic human speech. If you haven't heard some samples generated by WaveNet, I highly recommend you to go to their website, to the DeepMind's website. Samples are there, and have a look at them. The paper is also there if you're interested. So how do these fully visible belief networks work? They are actually based on the chain rule of probabilities. So they use that chain rule of probability to decompose an n-dimensional vector x, as you can see here, into the product of one-dimensional probability distributions. So now I think that you can see what is the problem of fully visible belief networks. In fully visible belief networks, for each step, we need to generate each step at a time. So first x1, the next 2 given x1, and the next 3 given x1 and x2, and so on and so forth. And also because each step is depends on the previous step, so there is no way that we can parallelize these steps. And because of that, fully visible belief networks are extremely slow. And the other thing that we need to know is that in modern fully visible belief networks, like the WaveNet, each one of these steps is computed by a deep neural network, and as a result, each step requires a massive amount of computation. And so, because of that, these models modern fully visible belief networks are unbelievably slow. For example, WaveNet requires 2 minutes of computation to just generate 1 second of audio. So GANs, unlike fully visible belief networks, don't have this problem. The other class of generative models that we consider them as GANs competitors are variational autoencoders. In variational autoencoders, we define usually a lower bound and a log likelihood. And so a learning algorithm that maximizes the lower bound is guaranteed to obtain at least as high a value of the log likelihood as it does of the lower bound. What are the drawbacks of variational autoencoders? One of the things that we know in theory is that when there is a gap between the lower bound and the log likelihood, then a P model tends to learn something other than P data, which is not good. But in practice, it actually never happens. So variational autoencoders often obtain very good log likelihood of the data. And there is another problem in practice that unfortunately we don't have any explanation for it in theory, and that is the quality of the images or samples in general generated by variational autoencoders is usually low. And this is not the problem with generative adversarial networks. So usually with generative adversarial networks, we can produce high quality samples. Now let's get to the exciting part, how generative adversarial networks work. Generative adversarial networks are, in general, can be considered as a game between two players. And you see in this figure, you see those two players. One of them is called generator, and the other is called discriminator. The job of the generator is to create samples that are intended to come from the same distribution as the training data. But the interesting thing that you can see in this figure is that generators do not have access to the original training data. The input to the generator is just a vector of random variables in the latent space, which we represent them with Z. And on the other hand, the discriminator has access to the training data as well as samples generated by the generator. And its job is to distinguish what is fake and what is real. By fake, we mean images generated or samples generated by the generator, and by real, we mean samples coming from the training data. Goodfellow and his collaborators, you know that Goodfellow is the father of generative adversarial networks, provided a very good example for generative adversarial networks, these two players. He said that we can think about the generator as a counterfeiter trying to make fake money. And on the other hand, the discriminator as a police officer trying to catch fake money and allow the real money to pass. Now, for the generator to win this game, what does the generator need to do? The generator needs to fool the discriminator. And in order to do that, so the job of the generator is to create samples that are drawn from the same distribution as the training data. Okay, so now we know that GAN is nothing but just a game between two players, generator and a discriminator. But what are these two these two players? They are actually nothing but just a simple, well, not very simple, but a deep neural network. But they're a bit different with the typical deep neural network that we are familiar with and using in classified cases. Each one of these two had a cost, as you can see here. A J superscript D represents the cost of the discriminator, and J superscript G represents the cost of the generator. And what is exciting about a generative adversarial network is that the cost of each one of the players not just only depends on the parameters of that player, but also on the parameters of the other player. For example, the cost of the discriminator not only depends on the parameters of discriminator, which we represent them with theta superscript d, but also to the cost of parameters of the other player, which we represent with theta superscript g. And the same story is about the generator. And what makes it even more exciting is that, okay, so now generator tries to minimize the cost, a discriminator tries to minimize the cost, but they only can control their own parameters and have zero control over the other player's parameters. And that's why this scenario is most straightforward to be described as a game rather than as an optimization problem. And we know that the solution to game is a Nash equilibrium, not an optimization problem. So the whole job of training in GAN is to find the Nash equilibrium of the game. And how we can do that? So this is the way that we train a generative adversarial network. First, let's say we have batches of size 100. So we take 100 samples from the data set. We take 100 samples from the latent space. And then we take one gradient step in order to update the parameters of discriminator to reduce the cost of the discriminator, and at the same time we take one gradient step to update the parameters of the discriminator to reduce the cost of the generator. And now, what are these costs? We said we want to minimize the cost, but what are these costs? So, first of all, I think that now you agree with me that the discriminator is actually nothing but just a binary classifier. And because of that, we can easily write the cost of the discriminator as the cost of the discriminator with a standard cross entropy cost. So here X is the input that we have from the training data, and dx represents the output of the discriminator when we have the sample up from the training data, which should be 1 because the X is real. And here Z is a vector in the latent space, and gz is the sample generated by the generator when receives that latent vector, and dgz is output of the discriminator when receives the sample generated by the generator, which we know that it's fake, and as a result inside log we have 1 minus dgz. Now, okay, so we know what is the cost of the discriminator, but what is the cost of the generator? If we consider the simplest possible game, which is we call it a zero-sum game, the sum of the cost of all the players should be equal to 0. And because of that, we can easily now define the cost of the generator by flipping the sign of the cost of the discriminator, and as a result we get this one. And now because the cost of generator ties directly to cost of the discriminator, so we can summarize this whole entire game with a value function and represent that value function here. Now, one exciting thing about this value function is that, okay, we just replaced this value function with the equation of the cost of the discriminator, but by negating the cost of the discriminator. And here I assume that the discriminator is optimal, and I replace just D in that equation with D star, which is the optimal discriminator. And then here we know that GZ is a sample generated by the model generator, so I just replace this bit with X, and now I assume that X is coming from P model. And then I don't have time to go through this, but if you're interested, you can refer to Goodfellow's paper, which is about generative adversarial networks. We can easily replace this optimal discriminator when input is coming from P data with this ratio, and this one with this ratio. And based on the definition of the KL divergence, which I just wrote it here as a reference, we can replace that line with this line. And then based on the definition of the Jensen-Shannon's divergence, we can replace this line with the last line. So now this is the exciting part. Now we just showed that to find the optimum solution for the value function, we just need to minimize the Jensen-Shannon's divergence between the data and the model distribution. And there is something exciting about Jensen-Shannon's divergence, and that is its value is always positive or equal to 0. So, and when it's equal to 0, when these P and Q are equal to each other. So we just showed that, okay, so this value function has a global optimum, and that global optimum is equal to -4, and it can be only achieved when P data is equal to P model, and that's exactly what we want from a generative model. We want the generator to generate samples that are coming exactly from the same distribution as data. We want P model to be equal to P data. But there is something, unfortunately, you know, when you try this in practice, then you see that your model doesn't learn, and that's because usually in generative adversarial networks, the discriminator has a tendency to become very strong. When it becomes very strong, then the generator's gradient vanishes, and as a result, the generator doesn't learn anything anymore. So to solve that problem, instead of flipping the sign of the discriminator and defining the cost for the generator, we flip the target, which I just wrote it here. And so now, previously, the goal of the discriminator, the goal of the generator was to minimize the likelihood of the discriminator and being correct. Now in the new definition, the job of the generator is to maximize the likelihood of the discriminator being mistaken. And unfortunately, because now JG and JD don't tie directly, then we cannot summarize this whole game with a value function, a single value function. And keep that in mind that this version of the game is heuristically motivated rather than motivated by theoretical concern, unlike the previous one. And the sole motivation for this version of the game is to ensure that each player has a strong gradient when the player is losing the game. Do I have time to go through? I have 3 more slides. Do I have time to go through? 5 more minutes, excellent. Okay, so as I said before, it is very hard to train generative adversarial networks. There are some tips and tricks in order to be able to train a generative adversarial network. First of all, as I said, they are most of the time we use, the majority of the time we use a convolutional neural network to model the discriminator and to model the generator. If you follow the practical, follow the tradition that we train a convolutional neural network, that convolutional neural network doesn't work in a generative adversarial network setup. So what is recommended? It is recommended that in the discriminator, instead of using ReLU as activation, use Licky ReLU. It is okay to use ReLU in the generator, but for the last layer, do not use ReLU. Use hyperbolic tangent. We usually use a few fully connected hidden layers at the end of the model in a CNN, in a convolutional neural network. When you're dealing with GANs, do not use them. And also, we usually in a CNN, in order to downsample, we are using a pooling layer after each convolution layer. For example, you usually use maxpool. So do not use maxpool. Instead, use a convolution with a strides greater than 1. And for the generator, because we are moving from a low-dimensional latent vector to high-dimensional image or sample in general. So to do upsampling, use a transposed convolution with strides greater than 1. And also, it is highly recommended to use batch normalization in every layer except the last layer of the generator and first layer of the discriminator, and because we want the model to learn the mean and a scale of the data distribution. And at the end, the best optimizer so far that you can work with is Adam, recommended by so many people. So when you're working with GANs, use Adam. And my last slide, as I said, I mean, those recommendations are to use when you want to train the generative adversarial networks. If you don't follow those recommendations, your model crashes during training and you can't train a model. But the quality of the image, even when you follow those recommendations, is usually not good. So there are some other recommendations, sometimes works for some people, sometimes doesn't work. So, you know, just don't try it, but don't think that it always works. One of them is using virtual batch normalization. Unfortunately, because now we are feeding two big convolutional neural networks to the memory of the GPU, so we don't have enough memory for data to train the model. And because of that, our mini batches that we are training our data is very small. And when the mini batch size is very small, then the statistics of that very mini batch fluctuates a lot during the training. And it seems that that fluctuation has more impact on the output of the generator than the impact of the latent vector to the generator. So to solve that problem, we are using virtual batch normalization. And what is virtual batch normalization? You can, at the beginning of the training, set aside a mini batch. And for each step of the training, so you grab one mini batch, combine it with the reference mini batch, you drive its statistics, mean and variance, normalize your data, but this time don't use the reference, just use the mini batch that you picked and train your model. The other thing that is recommended is training with labels. So we just said that we can use a GAN plus, you know, a typical classifier and train by using just a small portion of data labeled. The other way is also true. So if you label the entire data of your training data and then replace that discriminator this time again with n+1 classifier, which one class belongs to the samples generated by the generator, and then label your training data and train a model, it seems that the quality of the image is much better and more appealing to the eyes of the human. And the last one, usually when we train a generative adversarial network, as I said before, the discriminator has a tendency to become very strong, and when it becomes very strong, then the gradient, it doesn't help the generator to learn anymore. So because of that, we are using one-sided label smoothing, which means that we do not use label 1 for the outputs of the, training data. Instead, we are using something less than 1, usually like 0.1, 0.9, to train the model, and this kind of solves that problem. Thank you, and I don't think we have time for a Q&A, do we?
No, I'm afraid we don't. Please join me in thanking NEJLA for a great talk. Thanks. Well, now it's our customary announcements time, and pride of place, as always, goes to Greg Pearl from NWorld, who has a few things to say, I'm sure.
I do, I always do. Good to see everyone here, very good turn up. So Greg Pearl from NWorld Recruitment. I think a lot of you know me. If you don't know me, I specialise in data science recruitment across a range of different areas. I work with large corporates. I particularly work in the startup space. So jobs that I've got on at the moment, definitely team leadership roles, roles around artificial intelligence, social media. It's really a fact of coming and having a chat to me, telling me a bit about yourself, what you're looking to do. I can talk to you about the market, talk to you about where you might fit in that market and if there's any opportunities there for you. While I'm here, if I can just also say thanks to Troy and Kate for videoing tonight. If you go to the Data Science YouTube site, there's probably upwards of 20 past presentations if you'd like to go back and look through them. They're very good. This one will be up in the next few weeks. So hope you had a good night.
Do we have any other announcements? Cash.
Hi everyone, I'm Kashish from InfoPeople. I'm a recruiter too in the data science space. At the moment, I'm working on a number of data engineer roles. I've got permanent and contract both, so if you've got anything more than 2 to 3 years of commercial experience and if you're looking to move, please come and have a chat. And lots of them, about 15 roles at the moment, so please feel free to come and have a chat. Thank you.
Also, a very special announcement from Mark from Data Robot, who just did a sponsored presentation just a couple of weeks ago. Mark wants to some technological enhancement. Yeah?
Or not.
No, it's not a Mac, is it?
It's a Mac, yeah, okay.
It is a Mac. Oh, that's fine. Just put that in there. Can't you just put that in there?
This is a modern one there.
Oh, yeah. All right, just talk.
So I'll just talk. I wasn't going to spend a lot of time anyway. As Eugene said, I'm from Data Robot. We're an automated machine learning platform. We are based in Boston, but we've just opened up an office here in Sydney. We're looking for a customer-facing data scientist. That means someone who is interested in working with customers from large enterprises to smaller organizations such as fintechs. It doesn't mean necessarily that you're going to be making models and putting them into the product itself. We're looking to find people that want to apply your problem-solving skills and put them in the hands and help customers understand what machine learning is, the benefits of it, and obviously help get more of Data Robot out there in the field. So you're not expected to sell, that's my role. And you're just expected to do presentations, to help them with problem solving, and find unique solutions for our customers out there. So if you do or are interested, datarobot.com, there's a section that says we're hiring, there's a section that says Australian customer-facing data scientist, or you can look me up on LinkedIn, I'm Mark Shoebridge, and reach out to me there. So thank you.
Thank you. And thank you, Mark and Data Robot, once again for your recent sponsored event. And the next presenter is my new neighbour at Zetland, Sachin, who, if you want, we can get a lift back together.
Yes, please. Hi, everyone. So my name is Sachin, and just want to announce a new meetup that I'm doing. So it's called deepschool.io. So what's different with that meetup is that there's not going to be any presentations. Well, there might be a 10-minute talk if anything, but it's all going to be hands-on machine learning. So, sorry, hands-on deep learning. So you do need to have a bit of Python knowledge, and maybe a bit of knowledge on regression. But so on the 16th of Saturday, we're going to have a first meetup, and it will be good if you can join. And so in terms of levels, it's I've got tutorials all the way from beginners, hopefully advanced. So if I have time, I might do a GAN tutorial as well. So yeah, so come talk to me. I'll post a comment so that you can find the link. But yeah, thank you.
One more?
Hey, I'm Steph from Expert 360. We're a late-stage startup marketplace connecting consultants to project-based work. And we're not that big yet, but we're like hiring a lot of data scientists. We're talking to one of our first machine learning guys, but we also have a lot of engineering roles, and that's not a data scientist role, but we're also looking for a product data analyst. So if anyone also is more like data analysis. Yeah, just feel free to contact me.
Surely there are no more announcements. There is. Anthony.
Just a quick one. I'm Anthony. I'm one of the founders of the Minerva Collective, which is a Data for Good charity. I know a lot of you have been involved with some of our events. The only thing I want to mention today is there's a hackathon on the 15th to 17th of September, so that's just over 2 weeks. The topic is called the Hack for Homelessness. So we've curated a whole lot of data, I think mostly open data, around homelessness in Sydney, and we're trying to kind of get together a whole lot of people to help try to solve that problem. We have some really great prizes as well, some kind of 4-figure monetary prizes, as well as incubation and things like that. So it should be really fun. If you're interested, please go to Vibewire. I'll put the address on the meetup site, but it's the Vibewire Hack for Homelessness.